Hi everyone. My name is Rémi de la Porte-Maturin. I'm from CA France. I'm a PhD student working on modeling hydrogen retention, hydrogen transport, not in plasmas, but in solids. And today I'm going to guide you through how we can bridge what you guys do best, which is doing plasma stuff, and what we know is material sciences. Right. So this is ITER. That big guy here is ITER. That's for those who don't know, that's a tokamak, a fusion reactor being built in the south of France. So in a fusion reactor, we'll have a plasma of deuterium and tritium, and obviously producing some helium in it. The plasma will be diverted onto a component that's called the diverter in blue here. I hope you all can see my mouse moving here. All right, cool. So this component, the diverter, will be exposed to extreme fluxes of both heat and particles. And these can lead to several issues when it comes to tokamaks. First, we're dealing here with tritium, which is radioactive material. So we want to be able to keep tritium as low as possible in the solids. Hydrogen can lead to embrittlement, and I'm going to show you a few pictures later on. We don't want that. That can reduce the lifespan of our components. And again, that's something that's a bit more interesting to you guys. It's recycling fluxes, sorry, that can lead to a loss of performances in your plasma. And again, that's not something we want. Right, so if I may, you guys know about all the plasma stuff, and I have a little confession to make here, is that I'm not a plasma physicist, so I don't know much about it. But what we do know about is hydrogen transport in solids and materials. So what I'm trying to do here is bridging the gap between our two worlds and see how we can all work together. Right, so what happens in the material when it comes to plasma wall interactions? So as you can see here, hydrogen can be implanted in the material, and as soon as it enters the lattice, it can diffuse in the lattice, and eventually it would get trapped at defects or impurities. If it's hot enough, it can come out of these traps and start diffusing again. Eventually, it can reach the surface again, recombine with another hydrogen, forming an H2 molecule, and go back to the plasma. That will cause a cooling of the plasma, which will eventually reduce the performances of our tokamak, which is not something we want. Additionally, as I said before, hydrogen can lead to damage of our materials. So these are two examples of, on the left-hand side, blistering, and on the right-hand side, hydrogen-induced cracks. Right, so I hope that I've convinced you guys that we need to keep track of where the hydrogen atoms are in our materials. We do have models to do that, mathematical models, I mean. So this is a what's sometimes called a thermokinetic model or a macroscopic rate equations model. It's pretty well established. So the idea is to discriminate between mobile concentration of hydrogen, the ones that diffuse in the lattice, and the trapped concentration. I won't go too much into details of that because that's not something you're interested in. But these are the equations that we're trying to solve. So yeah, this is a diffusion term. We have a trapping term and a detrapping rate, and all these equations are coupled together. And yeah, we're trying to solve it in a simulation code. Right. Going back to our diverter. So when we take a close look at this diverter, it's made of plenty of tiny bricks like this, which are made mainly of tungsten. So there's a tungsten substrate with a copper cooling pipe running through and a copper interlayer for compliance. And so to model these kind of components, we had to develop a new code, which is called Festim. Yeah, yes, because this problem is multi-material, multi-dimensional, and multi-physics, because as you guys will see, we have to solve the heat transfer equation. So yeah, we had to come up with a new code, which is called Festim, which stands for Finite Element Simulation of Tritium Materials. Yes, obviously it's based on finite element methods. So it's based on a open source software that is Phoenix. Don't know if you guys heard about it, but that's what Festim is based on. It's able to perform 1D, 2D, and 3D simulations, both solving hydrogen transport and heat transfer. And yes, it's able to perform multi-materials simulation, which is not the case of all the H transport codes that are available. If you do want more information on that code, you can check out that publication of 2019. Right, we're done with the boring stuff. Let's go to the results. So these are the kind of results that we can obtain with Festim. So on the left-hand side, don't know if you guys can see the video. It should be a video. Yeah, right, running. On the left-hand side is a map of hydrogen concentration in the monoblock that I told you about. So it's advancing in time, and we can see that the hydrogen is diffusing into the bulk. So this is the plasma-facing surface on top, and hydrogen is being implanted in it, and it diffuses and get trapped. On the right-hand side is the temperature field. So again, this is a plasma-facing surface where the heat flux is striking. So obviously we have a temperature gradient here. In a few words, what we observe is that we have a higher retention being how much hydrogen is trapped in the solid. We have a higher retention in the cold regions. And that's because it takes energy for the hydrogen to get out of a trap in the material. So what do we do with that? The idea is to use that concentration field, integrate it to obtain the total inventory of hydrogen. Oh, sorry. And that's what we're going to use to assess how much hydrogen is stuck in our whole diverter, in our tokamak. Right. So we've performed these simulations for plenty of surface conditions. So we made the surface concentration and the surface temperature vary. We've performed more than 600 randomly distributed simulations. And yes, we obtained obviously different retention fields, as you can see here on orange and red. The idea was then to compute the inventory for each of these points and to integrate it using a package called Inference Tools, developed by Chris Bowman, that is, I think, in the chat. So yeah, so thanks to this package, we were able to interpolate all these data to have a continuous law linking the inventory of hydrogen to the surface temperature and surface concentration of hydrogen. And that's something that's going to be really useful for us. Yes, again, if you want to know more about that, you can check out that publication, which details everything nearly. Right, the question is, how can we apply this to the whole diverter? Can it be done? The answer is yes, and I'm going to show you how. Right, so if we go back to our diverter in ITER, it's made of two targets, the inner and outer targets. And what inputs we have are distributions along these targets. So that's where you guys come in. Is like, for instance, if we take the outputs from SOL-PS code, this is the kind of distribution that we have. We can assess the distribution of the heat flux along the target, the distribution of the particle flux, and the distribution of the particle energy, both for ions and atoms. So the idea is to convert these inputs or outputs of the plasma codes in inputs that we can use in FESTIM in our simulation, and especially in that behavioral or that 2D continuous behavioral that I showed you earlier on. So that's how we do it. Oops, sorry, there we go. We're able to compute the surface temperature based on the heat flux with this law. I won't go into much details here. And we compute the surface concentration based on a relationship between the flux of particles and the implantation depth RP and the reflection coefficient R. And both these coefficients depend on the particle energy and eventually the particle angles. And based on these two surface quantities, we can obtain the inventory of our monoblock thanks to that behavior that I showed you earlier on. So yeah, that's an example for one distribution in orange. So we have the distribution of temperature on the top left, the distribution of surface concentration on the bottom right, and yes, a bit of both here. And if we project it onto our 2D behavioral, we obtain a distribution of the inventory along the target. And that's where things start to get interesting to us. Let's take back our ITER case. So that's a case where all these data is available on IMS, which is the database of ITER. So we took a few runs where we had the diverter neutral pressure varying. So we go from low diverter pressure in blue to high diverter pressure in yellowish here. And we observed several things. First, we observed, and that was expected, that the maximum temperature is obtained at the strike point here. That position corresponded to the lowest inventory here. And that's because even though the particle fluxes are pretty high in that region, since the monoblock is hotter, the particles tend to get released more easily. Hence, we have a lower inventory. The most interesting thing is what we obtained here at the middle, which is the distribution of the inventory. If we integrate this over the whole diverter in ITER, we obtain roughly an inventory of 14 grams of hydrogen, so deuterium and tritium, after 20,000 pulses, which is, believe it or not much compared to the limit. We have a limit in ITER, which is 700 grams of tritium, because it's a nuclear facility, right? So yes, that's the kind of results we were able to obtain with that package. There's a paper to be submitted soon. So yeah, stay tuned if you want more details on it. Right. If everything here is not really your cup of tea, that's not a problem at all, because we've bundled all of that in a Python package that is open source and that is accessible on GitHub. So there's the link. I don't know if I can put the link in the chat or if someone can do it. But yeah, it is open. It's freely available. You can use it. If it's missing a feature, please do raise an issue or even make a contribution. Contributions are most welcome on that new package. To install that package, for those who might not be familiar with Python, you simply have to run the pip install div h retention, because that's the package, div h retention. And if you want to use that package in some of your work, please consider citing that publication for now. Right. I just wanted to showcase a few examples that are available on the GitHub repository. We also have plenty of notebooks available in the documentation if you are interested in the examples. But yeah, that's the main usage. So you can simply define an arc length, so that's x here, a surface temperature distribution, T, and a surface concentration distribution, and simply use the compute inventory function from that package, given a given time, and that will produce that inventory. It's a bit weird, but that's because it was complete dummy values for the distribution. But yeah, that's as easy as that. You can also use it from files. So say you have an output file from one of your codes or from one of your simulations. Then yeah, you can simply well, you maybe have to write a small wrapper if it's not in the right format. But for instance, this is a file that come up from the IMS database of ITER. So yeah, you can simply use it like this and plot the results. And so yeah, this is the kind of results I showed you earlier on. We can do it for another diverter that's not the ITER diverter, but say the West diverter, which is the French tokamak in south of France. The target is slightly different, of course, but it's the exact same technique. You just have a distribution of temperature and a distribution of concentration, and that's all. You can even make fancy visualizations that aren't really useful, to be honest. It doesn't bring much more, but yeah, it's pretty cool, I think. So that's a 2D map of the inventory in the West diverter as if we were looking from above. Yes, as I said, there are plenty of additional examples that you guys can look up on the GitHub repository if you like, or in the documentations. Right, and that's all from my side. If you guys have any more questions, please do ask, or you can also send me an email. I've put my email here, or I think I'm in the Discord channel as well. So yeah, my name should be simply Remy or something like that. So please do send me an email or a message or anything. Thank you very much.